Don't say that while I'm recording, Alex. So, today we're going to discuss approximations of integrals. Okay? That's excited faces. Okay. So, you're going to be asked to do this in the AP test. It also has like applications in like programming and things like that. But let's just say we wanted to handle a super amazing integral like this. Okay? So we're approximating definite integrals. And we're going to exploit the fact that an integral really does two things. The first is the area, well, the signed area, right? The signed area between x squared e to the x and the x-axis. And it also represents the change in n antiderivative. No, n antiderivative. Right? Yes? It's very citrusy in here. Good. You don't want to get the scurvy. Okay. So, that's not new. Everybody knows that, right? No, not scurvy. That it finds the area between x squared e to the x, and it finds the change in the antiderivative. Cool? A lot of times what we've done in questions like this is actually found an antiderivative and found how much it changed. All right? So what we're going to do right now, though, is approximate it. So just for fun, let's just find out what this answer is in general. Okay? I'm going to use a calculator. Actually, I'm going to type that into here. Oh, it's already in there. Excellent. So I've typed that into y1. I'm going to integrate it from 0 to 2. Everybody is comfortable doing this. I'm telling you. It's 12 something, 12.7781, we'll say. So that is the actual area under the curve and change in the antiderivative. Same thing, okay? But the question we're going to get when we have to do an approximation is not what's it equal. They'll say approximate this integral with, and they'll tell you how to do it. Okay? So let's take a look at an example of that, and I'll show you how we're doing it. Why is my pen not working? Example. Huh? Okay. Approximate the integral from 0 to 2 x squared e to the x dx with, we have 4 basic ways that we're going to approximate integrals. Okay? 3 of them are Riemann sums, and they're with rectangles, and 1 of them is with trapezoids. We're going to do all 4 with this one question, which is nuts, because you're not going to do one integral 4 times. I'm just going to use this one question to show you the 4 different ways. Okay? So, we'll go A. I'm going to say a left-hand sum. Cool. Another way to write that is a left Riemann sum, is what they'll say. Here's what's really going on. Can I zoom out to what? Okay. So, you do not need to graph this function. All right, but I'm going to graph it to show you what we're actually doing. So, this function basically starts out here and just goes up super, super quick like that. We are really interested in, I'm going to erase this, but we're really interested in this whole area in here. Is everyone okay with that idea? That's what the integral is really asking for. Okay? What we're going to do, though, is calculate it, approximate it without actually doing calculus. Okay? That's called a numerical method. You're doing calculus without actually doing calculus. We're approximating it. So, they'll also tell you when they say a left-hand sum, they'll tell you how many intervals, subintervals to chop this thing up into. So we're going to take 0 to 2 and we're going to break it up into pieces. That's not for you to decide. They're going to tell you how many. I'm going to say n equals 4. So the wording on the actual question will be like with 4 subintervals or with n equals 4. That means you want to go from 0 to 2 in 4 steps. How big is each step going to be? 1/2. You're so good at this. 1/2, right? You're gonna make them equal because we want them to be equal. That's all. So 1 would be like right here. 1/2 would be like right here, and 3/2 would be like right there. Now, I'm going to write this in a different color just so it's a little bit easier to see. On each interval, we can think of the area as the area on that interval. That's it. Okay? What we're going to do on each interval is put a rectangle in there that is approximately the area under that curve. Now, this is not going to be a good approximation. That doesn't matter. It's because we make 4 subintervals. Okay? But let's take a look at like this interval here, from 1/2 to 1. If I put a rectangle in there, it's going to have a base of 1/2. Everybody see that? The height, however, I have to choose how high I want the rectangle to be. There are 3 basic ideas to choose the height. We could choose the height of the function on the left side. We could choose the height of the function on the right side. Or we could choose the height of the function in the middle. We can actually choose the height of the function anywhere in there, but they're going to say left, right, or midpoint. Because this is a left-hand sum, we're going to choose the height on the left-hand side of the interval, which is at 1/2. So we're going to say the rectangle we're using has this height right there. And we're going to draw a rectangle in there. Because the question said left-hand sum. Okay? So again, it's not up to you to choose left, right, midpoint. The question will tell you. Okay? Everybody good on why that rectangle is sitting there like that? That's on the interval. We're going to put 4 rectangles in here because there's 4 subintervals, okay? On the interval from 1 to 3/2, again, it's a base of 1/2, but I'm going to take the height on the left-hand side of that interval, which is the y value at 1. Okay? From 3/2 to 2, we're going to take the height at 3/2. So that puts this rectangle in here like this. Okay? I skipped the first interval, which is from 0 to 1/2, because what's the height on the left-hand side of that? 0. So we're going to put it in there. It's weird. Okay? But that's fine. Again, that's not up to you to say like that doesn't make any sense. Okay? We're just left-hand side. The left-hand side there is 0. Does it make sense that those red rectangles approximate the area under that blue curve? They do a poor job of it, but they approximate it, right? Is it an under or overestimate? Definitely under. You can see it's an underestimate. Okay, they're going to ask you that on the AP test probably. If they ask you to do a Riemann sum, they'll ask you under or overestimate. And we'll talk about the rules for that. But if you draw it, you're going to be able to see if it's under or overestimate. Okay, it's pretty simple. Okay, so anytime you approximate anything, you should write out the thing you're approximating, even though it's right up top. So the integral of that function is approximately equal to, and all I'm going to do is write the area for each rectangle, which is just the length times the width, the base times the height. The base of my first rectangle is 1/2, and I'm going to multiply it by, it's 0 there, right? I mean, but I'm not going to write 0. I'm going to write the y value at 0, which is f of 0. It happens to be 0 in this case, but it doesn't matter. Everybody with me? My next rectangle has a base of 1/2 and a height of the y value at 1/2. Okay? And I should technically label x squared e to the x as f of x. Like I haven't done that anywhere. Cool. So that way I can just write f. But you don't want to define, use a definition without actually writing out what it is. My next rectangle is 1/2 f of 1. And my next rectangle is 1/2 f of 3/2. Okay? And we are going to use a calculator to find that thing. So, because I've already put in x squared e to the x into my calculator as y1, I'm going to write this out as 0.5. The way you write, you can do f of 0 here. It's go in the vars, grab y1 out of the function list, and put parentheses 0 next to it. That does not mean y1 times 0. It means y1 of 0. The calculator recognizes you want to put a 0 into the function that's in y1. Okay? So we don't need, alternatively, you could find all these values and just write them out here. But I mean, you got to take it out like 6 or 7 places. I don't want to do that. The next rectangle was 0.5. y1 of a half plus 0.5 y1 of 1 plus 0.5 y1 of 1.5, 3/2. And we get 6.607. Okay. So you can do this on your own if you want. I hope everybody can put it into a calculator. That's my approximation. Yeah, it's like half. It's almost half of what the actual area is. The area is 12.7. Okay, 12.7781. Easy enough? You all feel comfortable with this? Great. Find the right-hand sum. I'm gonna write it out up here. You do it on your own too. I'm gonna draw out what it looks like, but you don't really have to draw it. Yeah, still n equals 4. Good question. Yeah, we'll do n equals 4 for all of these. No. So my right-hand rectangles are going to look like this. X squared e to the x dx is approximately equal to. So when you do this on the AP test or on a test in our class, you don't just want to put an answer. Write out what you're doing. That ensures you'll get a point for showing you know what's up, even if you make a mistake entering in your calculator or something. Not that you guys ever make mistakes. Old Alex 30% EPIN. So we got a half y1 and a half plus a half y1 at 1 plus a half y1 at 1.5 plus a half y1 at 2. That is 21. Seems really big. Did you guys get 21 something? Yeah, okay. 21.385. I thought it was something different. I did these yesterday with the other classes, and I thought that was a different answer, but it doesn't matter. Again, you can tell this is an overestimate. When you draw the picture, clearly it's an overestimate. The rectangles are above the graph, so it's more area in the rectangles than in the blue curve. Everybody see what's going on? Again, you do not have to draw these, but drawing them helps you see what's going on. Okay? They can also ask you to do a midpoint sum. Okay? So instead of taking the height at the left side or the right side, you take the height in the middle. So let's draw that out because sometimes kids confuse the midpoint sum a little bit. So let's do a midpoint sum with n equals 4. What's nice about writing these out, by the way, is that regardless of what integral you're doing, what function's actually in there, that is the right Riemann sum for any function from 0 to 2 with 4 intervals. Like that's it. Just put a different function and you get the same thing. Or different answer, but same idea. Okay. So for a midpoint sum, if we draw this out, let's continue using blue. Your function does this. 1, 1/2, 3/2, and 2. Chop it up. So if we're going to work with a midpoint sum, whatever, we'll do black. My first rectangle has a base of 0 to a half still. It doesn't matter where we take the height. The bases are all a half because we get 4 subintervals. But if I take the height in the middle, I need to find the y value at what x value? 0.25, a quarter, yeah. So that's right here. And then you draw a rectangle like that. That's what that rectangle looks like. Okay. The next rectangle is going to go from a half to 1, so still a base of a half. But now I'm taking the height at 3/4. Next rectangle, a height from our base of 1 to 3/2, but now the height is at 5/4. And then you take the height at 7/4 for this one. And although they don't look like they have the same width, they all have the same width. So we write the integral from 0 to 2 of x squared e to the x dx is approximately equal to, my first rectangle is a half, f of a fourth, plus a half, f of 3/4, plus a half, f of 5/4, plus a half, f of 7/4. Everybody okay with the fractions in there, just taking the midpoint there? Okay, and you're going to drop in all these values. So this is probably a dumb way to do this, but 2, so it's 0.5, y1 of 0.25, point second, insert 7.5, y1 of 0.75, what's this, 1.25? And then 1.75, close, chaboom. And you get 12.174. Okay, so the midpoint sum is usually a better approximation. Remember how for the left-hand sum, definitely underestimate, no arguing that. Right-hand sum, definitely an overestimate. They're not going to ask you if a midpoint sum is an over or underestimate. Okay, because it's harder to tell. Like with the concavity, you can figure it out, like where the area is. They're not going to make you do that. Cool? That's it. It's pretty straightforward. And then the last thing we're going to do is trapezoid rule. But before we do trapezoid rule, I've been glossing over some stuff about what integrals are really doing here. So I'm going to go back over just the notation we're using, what's going on. This is not crazy important for our purposes in this class. So you can just pay attention to this and hopefully it makes some sense. If you took like calc physics, like calc-based physics, or like a college level calc 1 for like math majors, they're going to get into this pretty heavily. Because there's a lot of math we're doing right now that I kind of skipped over why it's all working out. Okay, so does it make sense that if I wanted to find, let's say, like the area under this curve from A to B, one thing I could do is approximate it with rectangles, right? We just did that. Okay, if I did 4 rectangles, that would not be a great approximation. But I put 1,000 rectangles into this thing. Can you imagine that? Every single one of them, I'll draw a couple, would be stupid tiny, and it would be a fairly accurate representation. Does that make sense? Y'all see what I'm doing here? If I drew all of those in there, it would be a pretty good approximation of that. Okay, if I put 1,000,000 rectangles in there, it'd be an even better approximation. So what we're really doing there, every single one of those rectangles is a base times a height, right? Now, the base of it, I always made a half in our previous record or examples, but technically all that is a tiny change in x. Do you remember how we used change in x when we found slope? How did I write that? x2 minus x1, okay, which was called delta x. Remember delta y over delta x, change in y over change in x is slope. Yeah, delta x just it doesn't have to be in slope. It represents a change in x. That's what the base is. It's some tiny change in x. Okay. the y value of each rectangle, or the height of each rectangle, is going to be the y value at some point in that interval. Okay? That's just f. So they write it like this. They write x sub I, where x sub I just means the first x value, second x value, third x value. Like we did that before, a half, one, 3/2, 2. Okay? And delta x is usually the same thing, but it doesn't have to be the same thing. So they write delta xi, which is just the length of that interval. Okay? Because they could be weird. That's the area of one rectangle. What do I want to do with all the rectangles? I want to add them all up. Remember the notation to add up a whole bunch of stuff? It's sigma. Yeah, it's sigma. It looks like a big E. It's actually a big S for sum. Okay? It's a Greek S, capital S. Cool, usually the little guys like that, right? Adding them up. If I put in 100 rectangles, we would let I go from 1 to 100. Cool? Now, doing this in a college level math class where like you had to do all this math out, what you would have to do here, and we can do it in this class, it's just patterns. You find patterns for these functions that you can actually find these sums. I don't know if you remember back in pre-calc, we did like geometric series. There are patterns for those, you can add them up. There's patterns for n, like I squareds and I cubes and stuff that you can add up, like a whole bunch of them. Do you remember, so this is off topic, but do you remember how to add up like a bunch of like linear terms? Probably not. Like if we had 2, 5, 8, 11, ... See how these are all added by 3? That's a linear term. Okay, well, let's say we got up to 98. Okay, do you remember how to do this? It was the first term plus the last term. So if you want to add up that entire chain of numbers, you could add them all up one by one, which would take a long time. Or you could do the first plus the last, and then multiply by how many of them there are, and I showed you why this works last year, and then divide by 2. There's 33 of them. Okay? And that right there will give you the sum. So that's 100, right? So that's what? 3,300 over 2. What is that? 1650? No? Let's say 6. If I'm wrong, I'm wrong. Sorry, YouTube. 1650. That seems too big. Whatever. You can tell what they add up to without adding them all up. Okay? There are formulas for that. Is that right? Okay. Oh yeah, 50 times 33 makes sense. Okay. So there are other patterns in here that we could use. We're not going to get into that crap. Okay. But the important part is we're adding up all these dumb rectangles. Doesn't make sense that if Dhruva did 100 rectangles and Seth did 1,000 rectangles and Alex did 1,000,000 rectangles, they'd all be about the same answer. Okay. But what would end up happening is as you add more rectangles, right, Alex's answer is closer to the real thing. Okay. And if I kept putting it, now I cannot use rectangles right now to find the exact value because the rectangles won't approximate it completely. But what I could do is keep putting more and more and more and more in and see what it approaches, okay? So let's say the area in here was actually 12, all right? If you put 100 rectangles in here, you might get 11.9. With me? If you put 1,000, you might get 11.99. If you put 1,000,000, you might get 11.999999. What's it approaching? 12. What's that called when we talk about what something is approaching? A limit. Yeah, okay. What we really want to find, and we did the same thing with derivatives. We brought our points really close together to see what they're approaching. We want to see what does this thing approach as I make this number get bigger and bigger and bigger. That make sense? So what they really do, the way they write this is they put like some variable up here. And they say, what does this thing do as m goes to infinity? And that's what the actual area is. That's how they define it. Okay, now that is a cumbersome thing to do. All right, it turns out that the area under there is the same thing as the change in the antiderivative. And the reason that's happening is because of this. How do you find the area of a rectangle? Very good. Base times height. Okay, where the base is, get out of here. Why are you here? The base is really just the function values, right? And the height is really, nope, I got that backwards. This is the function values. And these are the change in x's. It turns out, that's area, that distance, which I'm using distance, but it can be any quantity that changes. How do you find, if I said I ran 10 miles an hour for 2 hours, how far did I go? 20 miles an hour, right? Rate times time. Rate, let's do time times rate because I got this backwards. How much time went by is actually change in t, and the rate I'm running at is actually a function. Okay? So rate times time and base times height end up being the same thing for us. Okay? The problem is this. If I told you I ran 10 miles an hour for 2 hours, you would say 20 miles an hour. But what if I said I ran 10 miles an hour for 1 minute, and then I sped up to 12 miles an hour for a minute, and then I ran 8 miles an hour for a minute? You'd have to find my total distance on each one of those intervals. All that is a bunch of rectangles being added up. It's the same exact math. Okay? So our notation, and this is what I'm really getting at here, I guess, is that this right here is an infinite sum, and it's a lot to write, so we use a big old S. And that stands for sum. That's why the integral sign is a big S. Okay? Delta x, which is a small change in x, well, if I put infinitely many rectangles in here, x doesn't really change. X is infinitely small. Do you remember what happened to our slopes when we went from the slope from one point to another to the slope at one point? How do we write our derivative? What do we call it? We don't write delta y over delta x. We write dy over dx. This stands for an infinitely tiny change in y divided by an infinitely tiny change in x. Okay? That's the same thing's happening over here. This delta x is getting infinitely small. So this becomes dx. And because f of x sub I, well, if we're doing infinitely many rectangles, I can't list out every single xi. We just say, yo, we want all the f of x's between a and b. And that's where that notation comes from. All right? And we exploit this relationship right here. So to find the area, we can just find the total change in the antiderivative. And that's why that works out like that. Okay? So that is just what, and we should have done all that stuff first. A lot of calc classes walk you through all that crap first. Okay? I just did all the important stuff, like the mechanics of it. So what we've done is a left-hand sum, a right-hand sum, a midpoint sum. The last thing you're going to be asked to do is to find the area based off of an approximation of trapezoids. Okay? So we're going to do the same exact thing. So D. But we're going to find the value, we're going to approximate the value using the trapezoid rule. So instead of using 4 rectangles, we're going to use 4 trapezoids. So I'm going to draw this out again just so you can see what the thing looks like. Cool. And again, n equals 4, just to keep it consistent. We're going to chop it up into 4 subintervals, just like before. But rather than choosing a height to go horizontally across that thing, I'll just do the one right here, from 1 to 3/2. We take this side and this side, and we connect them with a line. Okay? Now, usually, what you're used to seeing, like in a geometry class, a lot of times, trapezoids come like this, right? Where this is the height, this is base 1, and this is base 2. Cool? We've turned that sideways. But the height, so height is kind of like a bad definition in geometry. It's not how tall it is off the bottom, okay? Height in this particular case means how far apart are the bases. What's the height of that red trapezoid I drew up here? 1/2, right? 0.5. Everybody good with that? Base 1 is the y value at 3/2, right? And base 2 is the y value at 1. You guys see that? Okay. If we draw all our trapezoids, we have this one here. We have this one here. And the very first one ends up being a triangle, simply because one of the ends is 0, bases is 0. But that's don't worry about that. We're just going to treat it like a trapezoid with a base of 0. Okay? So the area in all those red trapezoids, which is approximating from 0 to 2, x squared e to the dx. Area of a trapezoid, folks. Yo, some of y'all are still doing a rectangle and a triangle and chopping this up. Don't do that. Use the area of a trapezoid. It's 1/2 the height It's 1/2 the height. It's just the same as a triangle, kids. It's the basis and the height times a half. That is it. You cannot use squares or rectangles and triangles here. It's not going to work. You have to use this formula. Okay? That's it. Add the bases, 1/2 height times basis. Okay? So in this case, my very first trapezoid is 1/2. The height also happens to be a half. That's okay. Times base 1. I'm doing this one right here, which is the y value at 0 plus the y value at a half. Everybody see what's happening? 1/2 is there because that's the formula part. The height is a half, and then the bases are the y values. Plus, I'm going to go down 1/2 times the height of 1/2. Now we're doing this second one here. The first base is f of 1/2, and the second base is f of 1. And we're going to get 4 of these because there's 4 trapezoids. Plus 1/2 times a half times f of 1 plus f of 3/2. And then the last one, 1/2 times a half f of 2. You doing okay? We're going to add all these up. Now, if you're going to put this into a calculator, and if you look in a textbook, they don't write it like this. They simplify this down. Okay? So I'm going to show you the simplified version, like the little formula you'll see in any calc textbook. But this only works if all of our intervals are the same exact width. Like all the heights of these trapezoids is a half, right? If the heights were different for some reason, then we cannot do what I'm about to do. Do you see that every single one of these trapezoids has a 1/4 out front, basically, right? A half times a half. If we factor that out, so this right here is the same thing as saying 1/4. All right, well, half times a half, really, right? As a half times a half. If we factor that out, times, and then all we have is always f values, right? So we have f of 0. And then technically we have plus f of a half here, right? But then in my very next trapezoid, we add another f of a half. Okay, so there's really 2 f of a halves in there. Yeah, plus we have an f of 1, but then the very next trapezoid has another f of 1. So there's 2 of those. Okay, there's f of 1 here. There's f of 1 here. Plus 2 f of 3/2. That's these two, f3/2, f3/2, and then plus f of 2. So that's like the shorthand way to write the trapezoid rule out. If I were you, I would use this right here. I know it's a little more writing, but it really shows you the trapezoids that are happening. And if the bases, the widths aren't the same, the heights aren't the same, then you can't do what I just did. What's up?
So you said only use the right side if the height is the same?
Yeah. So if you were given a function like I gave you, x squared e to the x, and asked to trapezoid rule in an interval, you can make them all equal. What the AP test does to us is sometimes they give you just a table of values. So they don't even give you the function. They just give you x values and y values, and they're not evenly spaced. That makes sense? So then I used to teach the formula, and kids would try to do the formula based off of that, and you can't. You just can't do it because they're not equally spaced. Okay? We'll look at one of those in a second. So we're going to put this in. Everybody put this into a calculator. What'd you get? 13. Point what? 996. Okay. So trapezoid rule is usually a better approximation as well than like a left sum or a right sum. Okay. There are other ways, like, so when you integrate on your calculator doesn't know calculus because it doesn't have like a computer algebra system built into it. But it can find areas, and that's what your calculator does. It does something a little more advanced, but it's basically putting a bunch of rectangles under that curve. Cool. There's another, so something I'm skipping over here. Let me just show you an example of this too, that I'm not showing you. So we use rectangles, we use trapezoids, which is better because it connects the things, okay? Somebody out there way back in ancient Greek times, we have the area of a circle, we have area of rectangle formulas, we have area of trapezoids formulas, right? Someone way back in the day said, man, if you have a parabola, like an exact parabola, not just a curve that goes down and up again, but a parabola, okay, and you want to find the area underneath of it, then you can use it using this formula. There's a formula for it. There's a formula to find the area under a parabola, okay? So someone came along with integrals and said, rather than connecting these things with a straight line, because it's not a straight line, right? It's a curve. Why don't we put a parabola right through here like that, and put a parabola right on this one, and put a different parabola right here on this one, okay? And then you find the area underneath those parabolas, which seems complicated, but it's really just a formula you can use and spit out. It's called Simpson's formula, okay? So that's there. A lot of calc teachers will teach that. It's not on the AP test. It's just a formula you got to memorize. I'm not going to get into it. But that's a much better approximation, okay? And your TI 84, 85, 89, whatever you're using, does something similar to that, but probably even quicker and better than that. All right. So that's that. I'm gonna shut this down. Feeling okay? We're gonna look at an AP question. Okay. Where's this? Right here. That was a long video.